Okay, so I was thinking to put this addendum at the end of the last lesson on linearization. I actually mentioned this example at the end of the lecture, but I didn't really finish the whole analysis, and I was thinking that maybe it's worthwhile if you're interested in how you actually handle an example in which the Jacobian method doesn't work. How does one go about figuring out actually the stability of the equilibrium? And I actually mentioned it in the previous lecture, but I want to finish or to give more details on this analysis. Again, that's actually optional. It's not part of the exam or anything, but this is one of those textbook examples in which certain topics are illustrated usually, in which you create an example to have a certain behavior, right? I mean, first of all, an example in which obviously the linearization doesn't work, because that's the goal. And to show that the stability can still be determined by other means, except that we don't have a nice recipe like the Jacobian. And of course, in real life, we don't actually have examples like this because they are designed backward in a way. I mean, from the result you're looking for, they are designed to have that property, and then the system is actually given so that it has that property. But if you go and study in more depth nonlinear systems, when you study the behavior of nonlinear 2x2 systems, you will see lots of examples coming from polar coordinates, because that's kind of the easiest way to produce many examples that with interesting properties in the nonlinear case. So I think it's worthwhile to go over the process on how you actually deal with, how you change it from Cartesian to polar coordinates, and how you actually prove the stability of an equilibrium point when the Jacobian doesn't work. So just to summarize, 0, 0 is an equilibrium point. The Jacobian, if you compute it, will have 0 real part. The eigenvalues will have 0 real part. So you cannot use linearization. So this system is suitable to polar coordinates. So remember, x and y stand for x of t, y of t. So you can move from Cartesian coordinates to polar coordinates. So you're going to have each point identified by a polar radius and the polar angle. Again, both of them depending on t, because this is a differential system, so as the solution changes, as the solution moves, then you have, of course, a variation in time of these coordinates. And remember that the relationship between the Cartesian coordinates and the polar coordinates is given by x equals r cosine of theta, y equals r sine of theta. Again, r sine, r theta, x and y are functions of t. And let's change the whole system into polar coordinates. And actually, in the previous example, in the previous part of the lecture, in the mandatory last part of this lecture, I did come up with the equation for r prime, but not for theta. And so that in that sense, the example was not complete. So keep in mind that you could always replace x squared plus y squared by r squared. That's one thing to keep in mind, right? When you add the two. And also, typically theta is given by tangent, because what one can do is divide y by x, so you have tangent of theta equals y over x. So one attempt to figure out the differential system in polar coordinates from Cartesian coordinates is to differentiate these equalities. So let me do this again just for completion. We did that last time, but let's do it again for r prime. So when I differentiate both sides, I get 2r prime, remember it's the chain rule here, equals 2x x prime plus 2y y prime. So you could divide by 2, and let's replace x prime y prime with the respective right hand side of these systems. So we have r times r prime equals x times, so instead of x prime, we're going to write y minus x times r squared. Notice, to save some time, I'm going to replace already x squared plus y squared by r squared. We can do that right away. And then plus y times y prime, which is minus x minus y times r squared. Okay, so let's simplify this a little bit. We have xy minus x squared r squared minus xy minus y squared r squared. So x and y canceled, and we can pull out now minus r squared, and you're left with x squared plus y squared, which is another r squared. So combined, they form r to the 4. We divide by r, both sides, and then r prime is equal to minus r third. Okay, so that's a simple equation in r of theta, r of t. Okay, so the equation. Now, most of the time, of course, the differential system will depend on both r and theta, but of course, this turns out to be a much easier example in polar coordinates. So, turns out that r prime happens to depend on r only. So, I mean, if you remember last time I said this shows that r goes to 0, but one has to be a little bit careful here because we need to figure out what theta does. Okay, I mean, what if theta, for example, stops at some point? Because as the solution moves, remember, theta measures how do you go around the origin. Okay, so theta increases counterclockwise, decreases clockwise. And this may show, for example, converges to 0 for the radius, but what if along the way theta stops, and then at some point, and then that means maybe the dynamic stops at some point? Because remember, this is a system. I mean, this doesn't live by itself. There is an equation for theta as well. Theta doesn't stop. That's the key, and this is essentially what I wanted to, my main reason why I wanted to go about showing this example fully. So let's obtain the equation for theta at this point, right? So let's go back to the tangent of theta and differentiate with respect to t both sides of the equality. Again, all of these are functions of t, so we have to use the chain rule. So when we differentiate with respect to t, both sides, keep that in mind, the chain rule. So on the left side, we're going to have secant squared, the derivative of tangent, times theta prime, or d theta dt. Here we have the quotient rule. So we have y prime times x minus y times x prime over x squared. So now we're going to do on the right hand side what we did before. We're going to replace y prime and x prime with their respective expressions in terms of x and y. And then hopefully we're going to be able to switch to polar coordinates when we're done. So secant squared theta times theta prime. All right, let's see, y prime times x. So it's going to be x times y prime, which is minus x minus y times r squared. Then minus y times x prime, which is y minus x times r squared. We're going to have some magic cancellations again, because the example was concocted, in fact, from polar coordinates to have these nice cancellations. So minus y times x prime, all good, divided by x squared, which in polar coordinates is r squared cosine squared theta. All right, so let's see what we have now. So we have secant squared times theta prime. On the top is minus x squared minus xy r squared minus y squared plus xy r squared over r squared cosine squared theta. So we have the cancellation of xy r squared, and notice minus x squared minus y squared, it's actually minus quantity x squared plus y squared, which again can be replaced by r squared. So secant squared theta prime, on the top here minus r squared divided by r squared, and notice I also have 1 over cosine squared, but 1 over cosine squared is nothing but secant squared. So this is minus 1 once you cancel r squared times secant squared theta. Again, it's always unfair when you read this, because you may think that, how come that happens? I mean, again, it's not like you start with random numbers here and then magically you have such a nice cancellation in polar coordinates. It is designed that way from polar coordinates and back. And maybe later on, maybe I'm gonna add some even more interesting examples again on how you start from polar coordinates with a behavior in mind for the solution, and then you're gonna show the system in Cartesian coordinates, and there you go, you have a nice example for the Cartesian coordinates. So now we can cancel secant squared, and so that's basically the conclusion, or the part that we want to get to essentially when we figure out the dynamics of the system. So the full system in polar coordinates is now completely decoupled. Okay, so I mean, this is the system in Cartesian coordinates. This is the equivalent system in polar coordinates r of t, theta of t. Not only is decoupled, the second equation, I mean, both equations can be solved very quickly. Okay, so let's see how we prove the stability of the origin now. I mean, if we start at a point anywhere in the phase plane, how do we show the solution actually approaches zero? Well, for one thing, let's actually solve the equation for theta. We just integrated theta prime of t equals -1. Integrate both sides. That's a calculus 2 problem. So we have theta of t minus t plus a constant. That constant, of course, depends on your starting point. For example, if I start here, it could be theta of 0 could be pi over 4, right? I mean, it doesn't matter, right? So the starting point will give you c, and the starting point for theta means the starting polar angle. But the bottom line, and that's the key thing, notice that the limit as t goes to infinity of theta of t is minus infinity. So what does that tell me in terms of the dynamics? Well, it tells me that any point you start with, the solution trajectory rotates around the origin indefinitely. So to say that your system in polar coordinates has an unbounded theta, it's to say that the solution keeps on going around the origin all the time, rather clockwise, right? Because you have minus infinity. But for our purposes, it doesn't matter whether it's clockwise or counterclockwise. Okay, so clockwise goes around the origin all the time. Again, we're not talking about what r does. Theta tells me that no matter where you start, the solution wraps around the origin and keeps on doing it without stopping. Without stopping, right? There's no stopping because theta of t goes to minus infinity. Keep on going around the origin. Okay, so at this point in time, what does the radius do? Well, for that, we can either solve this, but it's easier to just do a little phase line analysis. It's a single ODE in r of t. The equilibrium is 0. If I start with a point above 0, that's going to give me a negative derivative. So that's the phase line for r prime equals minus r third. So, 1 second. Smear this too much. All right, and then if you start with a point below 0, then this will be a positive quantity. Okay, so therefore this point is stable for the equation of the radius, of the polar radius. So while theta goes to infinity, so while you have those rotation, the polar radius approaches 0. And by default, I just described a stable spiral. Rotating around indefinitely, while the distance from the point to the origin keeps on decreasing until it approaches 0 in the limit sense. So that's how you, one way to figure out the stability without the Jacobian. Obviously, in examples that are not made to be nice, things are more complicated than that. There is a different way to figure out the stability, but one has to look at higher order derivatives in that Taylor expansion. So you can't just use the linearization. So again, this was just an optional if you're interested in more topics related to the nonlinear systems. And again, maybe I may add other topics when I have time later on as addendums. And thank you for your attention.